All right, the last topic in 4.4 is about these indeterminate powers. Now, indeterminate powers come in three flavors. You've got 0 to the 0, 1 to the infinity, and infinity to the 0. In all these cases, what's going on is a fight between what the two things are trying to do. If you have just the number 0, that's going to, be 0. But we also have the rule about anything to the 0 is 1. So this one's going to be a fight between whether whether the limit goes to 0 or 1. On this, if we've got 1 to the infinity, this number up here is growing, large, and so and this number here is just 1. So the 1, it's like it's going to try to make the thing 1, because if you take 1 and raise it to any power, you get 1. However, if the 1 is approaching from below, then you've got some number smaller than 1 raised to the infinity. That's going to try to go to 0. If the 1 is approaching from above, you've got a number bigger than 1 raised to the infinity, and that's going to try to go to infinity. So what we're going to have there is a fight between those values. And down here, infinity to the 0, the infinity is going to try to make this grow large, and the 0 is going to try to make it go to 1. So in all these cases, we've got some kind of fight going on between the two functions. And I want to talk about how to resolve that. For any of these three kinds, if it's indeterminate and you have this form, what you do is you, instead of taking the limit of the original thing, you basically take the natural log of it. We're just going to call that y equals that function. So you take the natural log of both sides, then you do the limit of natural log of y. And what that gives you is, instead of your final answer, it gives you L, which is the limit of the natural log. And at the end, you do e raised to that L, and that gives you the limit of the original function. So I've got 4 examples here I want to do. This first one is x is going to 0 from the positive side. So this one is a 0 to the 0 type. So let's work on it. I'm going to let y equal x to the x. So I get ln y equals x ln x. All right, so I skipped a step there. Let me go back. You get ln of x to the x, and of course you can rewrite that as x ln x. So now what I need to do is take the limit as x goes to 0 from the plus side of x ln x. Okay, well, x ln x, that is, if we're going to 0, the x here is approaching 0, and ln x is approaching minus infinity. So we've basically turned it from an indeterminate power into an indeterminate product. So what we'll do is rewrite this like we did before. We got x going to 0 from the plus side. I'm going to make this ln of x on top and 1 over x on bottom. And now what we've got here is an infinity over infinity type. Technically this one's negative infinity, but it doesn't really matter. You can still run L'Hopital's rule on it. So L'Hopital, I'm actually going to take this up here to finish it. Let's see, L'Hopital, we get x goes to 0. On top, the derivative of natural log is 1 over x. On the bottom, the derivative of 1 over x is minus 1 over x squared. And so what we've got here now is infinity over infinity, but we can simplify this one algebraically quite easily. So x goes to 0. And let's see, on top we've got 1 over x, and then we divide by 1 over x squared, so it's times x squared over 1, and I've got to put a negative somewhere in there. So what we've got here is the limit as x goes to 0 from the positive side of, this is just negative x, and what do we get there? It's just 0. And so that's not quite our final answer. For our final answer, what we have to do is e to the 0. That gives us 1. So our answer here is just 1. And we can check this by looking at Desmos. let's see, I've already got this graphed on Desmos. Here we go. If you look at this and you trace along this graph as x gets close to 0, y approaches 1. So sure enough, it works. All right, we've got several more examples, and let's see. Let's go ahead and break this up. I'm going to do 2 examples in this video and 2 in the next video. So let's see, as x goes to 0, so you let y equal, well, first off, is this indeterminate? Well, when x goes to 0, sine x goes to 0, and x goes to 0. So this is a 0 raised to the 0 type. So let's see, I'm going to let y equal ln of sine x to the x. So, well, let's see, y is equal to that, and then we're going to take the ln of both sides. So you get ln y is x ln sine x. And let's see, is this still a, if I write this now as a limit is x goes to 0 of x times ln sine x. This is indeterminate because what we've got here is this is 0 and ln of sine x, well, the sine x itself goes to 0 and ln of 0 goes to negative infinity. So we've got 0 times negative infinity, so sure enough, this is indeterminate. Now let's see, what can I do to this to make it better? I could either rewrite it, x goes to 0 from the plus side. I could either keep natural log of sine x on top and move this to 1 over x on bottom, or I could do limit as x goes to 0 of, keep the x on top and then put 1 over ln sine x on bottom. This is much more complicated, so let's don't do that. For a second there, I was thinking about maybe we could use cosecant by moving the sign down bottom, but that doesn't work because the sign is trapped inside of that natural log. All right, so let's do this with L'Hopital's rule. If I take L'Hopital's rule here, on the top, natural log of sine, so sine goes to the bottom, its derivative goes on top. And then downstairs we've got 1 over x. You take the derivative of that, you get minus 1 over x squared. All right. Let's see, what do we get here? Tangent of cosine over sine is cotangent. But let's rewrite it like this. X goes to 0 from the plus side. Let's see, on top we've got cosine x over sine x. And then we're dividing by this 1 over x squared, so I could put the x squared on top and the negative 1 on bottom. So we get this. What about now? It seems like we're kind of in trouble. If we plug in the 0, well, we're not in trouble, it's just we're not done yet. If you plug in the 0, down here you get 0, and up here you get 1 times 0. So, looks like we got to use L'Hopital's rule again. So if I take L'Hopital's rule again, let's see, on the bottom, let's see, this is still limit as x goes to 0. On the bottom, it's easy. Derivative of sine is cosine, so this is minus cosine x. And this looks promising because if we plug the 0 into the bottom now, we're going to get 1. On top, though, we've got to use the product rule. So we get first times derivative of the second plus second times derivative of the first. Now, derivative of cosine is negative sine, so I'm going to come back up here and change this to a minus. Okay, so what if we plug in the 0 now? Let's see, if we plug in the 0, over here we get, that's just going to be 0. I'll tell you what, I'm going to write this above here. Cosine of 0 is 1 times that gives us 0. And over here, we've got 0 times 0, which is also 0. And on the bottom, we've got 1. So our answer, at least to the natural log of this, is going to be 0. And so that means the answer to our original problem is e to the 0, which again is 1. So that's a lot of work to just get a 1 for your answer. But let's compare that to Desmos. If we look on Desmos and look at this graph, this is it here, sine x. Let me make sure I've got this written correctly, because this is supposed to be sine of x raised to the x power. I think it's right, but let's just double check. Yeah, it's kind of an interesting graph. But if you look at this and you approach as x gets close to 0, or y gets close to 1. So that's right. All right, we got 2 more examples, but I'm putting those in the next video.